Hi there, and welcome. In this session, we'll be tackling LeetCode problem number 117, populating next right pointers in each node 2. This problem challenges us to work with binary trees and efficiently connect nodes at the same level. Get ready to explore the concepts, approaches, and techniques needed to solve this interesting problem. Let's dive in. In this problem, you are working with a binary tree where each node includes an extra pointer called next. The purpose of this pointer is to connect each node to its next right neighbor on the same level. If no such neighbor exists for a node, its next pointer should be set to null. Initially, all of these next pointers are set to null. Your task is to update these pointers so that each one correctly points to the next right node, or null when there is no neighbor on the right. Importantly, the solution must be implemented in place, meaning you cannot use extra data structures to store nodes during the traversal. The input will consist of the root of the binary tree, and each node will have properties such as its value, references to its left and right children, and the next pointer, which starts as null by default. The output of your function should be the root of the binary tree after all the next pointers have been populated correctly. Let's look at an example to clarify. Consider a tree where the root node is 1, with 2 and 3 as its left and right children respectively. Node 2 has 4 and 5 as its children, while node 3 has a right child 7. In the output, the nodes should be connected as follows. On the first level, node 1 points to null. On the second level, node 2 points to node 3, and node 3 points to null. On the third level, node 4 points to node 5 points to node 7, and node 7 points to null. Breaking this down further, on level 1, the root node 1 does not have any right neighbor, so its next pointer remains null. On the second level, node 2 connects to node 3 using its next pointer, while node 3 does not have a right neighbor, so its next pointer is null. Similarly, on the third level, node 4 connects to node 5 connects to node 7, and node 7, having no right neighbor, points to null. Another example is a simpler tree where the root node 1 has 2 as its left child and 3 as its right child, and node 3 has a right child 7. Here, node 2 connects to node 3, and node 7 points to null since it's the last node on its level. Taking this explanation further, in the simpler tree where node 1 is the root, we observe that node 2 still points to node 3, and node 3 does not have a right neighbor, so it points to null. On the final level, node 7 also points to null since it has no right neighbor. In the simplest case, if the tree contains only the root node, for example, a single node 1, its next pointer remains null because there are no other nodes in the tree to connect to. This illustrates how the next pointers are determined at each level based on the given structure of the tree. There are a few important constraints to keep in mind. The tree can have up to 6,000 nodes, and the value of each node will fall within the range of -100 to 100. Your solution must be implemented in place, meaning you cannot use additional data structures to store nodes during traversal. Additionally, there are edge cases to consider. If the tree is empty, meaning the root is null, the function should simply return null. If the tree consists of only one node, its next pointer should remain null. Finally, for nodes that have only one child, the next pointer should be assigned correctly for the existing child, ensuring that the solution handles all possible scenarios. To solve problem number 117, our goal is to link each node in a binary tree to its next right node on the same level. If there's no adjacent node, the next pointer should point to null. Unlike problem number 116, the tree here isn't guaranteed to be a perfect binary tree, which introduces additional complexity. One approach to address this is the brute force method using a level order traversal with the help of a queue. The idea is to process the binary tree level by level, connecting the next pointer of each node to the subsequent node in the queue. This involves storing nodes for each level in the queue, iterating over them sequentially to establish the connections, and moving down level by level until the entire tree is processed. While this approach is easy to understand and has a time complexity of O(n), since each node is visited once, the space complexity depends on the maximum width of the tree, which could be as much as O(n) in the worst case, such as in a full or very wide tree. However, the brute force approach, while intuitive, does come with trade-offs, particularly because of its additional space requirements for storing level information in the queue. A more efficient solution is the optimized approach that uses constant space, leveraging the existing next pointers to traverse the tree. Here, instead of relying on external data structures, we use a dummy node to dynamically manage connections at the next level. This approach starts at the root and iterates through the current level using the next pointers already established. For each node, its child nodes are linked using the dummy node, which acts as a placeholder for the beginning of the next level. Once the current level is complete, we move to the next level using the next pointer from the dummy node. This process repeats until all levels are processed. With a time complexity of O(n), as each node is visited only once, and a space complexity of O(1), since no additional data structures are used, this solution is both space efficient and scalable. The trade-off here is implementation complexity, as it requires careful management of pointers and levels. The optimized approach using constant space is the preferred solution for this problem. Its key insight is recognizing that the next pointers themselves can be used to traverse the tree, eliminating the need for extra memory like a queue. The dummy node simplifies the process of connecting children across levels, making it both elegant and efficient. This approach excels in scenarios involving sparse or unbalanced trees, where other methods might struggle. The space efficiency of O(1) is particularly advantageous for handling larger trees, and the time complexity of O(n) remains comparable to the brute force method. In summary, while the brute force approach is easier to conceptualize, this optimized strategy strikes the perfect balance between efficiency and complexity, making it the most effective choice for solving this problem. In this problem, we aim to populate the next pointers for each node in a binary tree. Each node's next pointer should point to the node immediately to its right on the same level. If there's no node to the right, the next pointer should be set to null. Unlike the previous problem where the tree was perfect, here the tree can have gaps, meaning some nodes may be missing along the level. To solve this, we use a level order traversal approach that processes the tree one level at a time. The key idea involves using a dummy node to help link nodes on the next level, even when the tree has gaps. We start with the root node, and if it's null, we simply return since there's nothing to process. Otherwise, we initialize our dummy node, which acts as a placeholder for the start of the next level, and a current pointer to traverse the nodes at the current level. The traversal proceeds iteratively through each level of the tree, ensuring all next pointers are established before moving to the next level. To process each level, we reset the dummy node's next pointer to null and use a pointer called tail, which starts at the dummy node. The tail pointer helps build the next pointer chain for the next level. Now, we use a current pointer to iterate over the nodes of the current level, using the next pointers that were already established. For each node, we check if it has a left child. If it does, we connect the tail dot next to the left child and advance the tail pointer to this new node. Similarly, if the node has a right child, we connect tail dot next to the right child and move the tail forward. Once we've processed the current node, we move the current pointer to its next node, repeating this process until we traverse all nodes on the current level. After finishing the level, we move the current pointer to dummy.next, which now points to the first node of the next level. This process continues until there are no more levels to process, meaning current becomes null. Special cases include an empty tree, where we return null immediately, and sparse levels where some nodes may have only one child or none at all. The dummy node plays a crucial role in simplifying the linking process. By acting as a placeholder for the beginning of the next level, it eliminates the need for additional checks to determine the first node on each level. This approach also optimizes space usage compared to a traditional queue-based level order traversal. Instead of using O(n) space for a queue, we leverage the next pointers to traverse the tree, achieving O(1) extra space. The algorithm follows a breadth-first strategy, ensuring that all next pointers for a level are set before moving to the next one. To implement this, we rely on three key pointers: the dummy node to establish the next level, the tail pointer to build the next pointer chain, and the current pointer to traverse the current level. In terms of complexity, the time complexity is O(n), since every node is visited exactly once. The space complexity is O(1), because no additional data structures are used beyond these pointers. For example, consider an input tree where the root node has 2 children, and subsequent levels have varying numbers of children. Using this approach, we handle such structures efficiently while maintaining the correct next pointers. Let's walk through an example to see how the algorithm works. Starting with the root node, which is 1, we initialize the dummy node and the tail pointer. We then process the children of node 1, which are nodes 2 and 3. The next pointers are set such that 2.next points to 3, and 3.next points to null. Next, we move to the second level, starting with node 2. Here, we process its children, nodes 4 and 5, and then process node 3's child, node 7. The next pointers at this level are established as 4.next pointing to 5, 5.next pointing to 7, and 7.next pointing to null. At the third level, starting with node 4, we observe that there are no children, so the traversal terminates. At the end of this process, the final tree structure has next pointers such that nodes at the same level are connected, while the last node in each level points to null. This ensures the algorithm handles both sparse and complete levels seamlessly. Here, we define a node class to represent each node in the binary tree. Each node has a value, along with pointers to its left and right children, as well as a next pointer that we will populate. Then, in the solution class, we define the connect method. This method starts by handling the edge case where the input tree is empty, immediately returning none if the root is null. Next, we initialize 3 pointers, next_level_head to track the start of the next level, next_level_cur to build the next connections within the next level, and current to traverse nodes in the current level. The outer while loop ensures we process each level as long as there are nodes to visit. Within this loop, we use an inner while loop to traverse all nodes in the current level. For each node, we first check if it has a left child. If it does, and next_level_head hasn't been set yet, we initialize both next_level_head and next_level_cur to this left child. Otherwise, if next_level_head is already set, we simply update the next pointer of next_level_cur to point to this left child. After pointing to the left child, we move next_level_cur forward by assigning it to its own next. Then, we check if the current node has a right child. Similar to the left child, if next_level_head hasn't been set yet, we initialize both next_level_head and next_level_cur to the right child. Otherwise, we update the next pointer of next_level_cur to point to the right child and move next_level_cur forward. Once we've processed both children of the current node, we advance the current pointer to the next node in the same level using its next pointer. After finishing all nodes in the current level, we move to the next level by setting current to next_level_head, and we reset next_level_head and next_level_cur to none in preparation for the level below. Finally, when all levels are processed, the root node with its updated next pointers is returned. Here, we start with the definition of the node class, which represents each node in our binary tree. Each node has 4 properties: val for the node's value, left and right for its children, and next for the pointer to the next right node at the same level. The class also offers 3 constructors, a default constructor, one that initializes just the value, and another that initializes all 4 fields. After defining the node class, we move to the solution class where the connect method is implemented. This method takes the root of the tree as input and connects all nodes at the same level. The first step in this method is a base case check. If the root is null, we simply return null since there's no tree to process. Next, we initialize 3 variables to help us traverse and link the nodes. Current represents the node we're currently processing at the current level, while next level head serves as the starting point of the next level. Next level cur is a pointer we use to build the connections at the next level. We then enter a while loop, which continues as long as there are nodes to process in the current level. Inside this loop, we handle the left child first. If the current node has a left child, we check if next level head is null, which would mean this is the first child we encounter at the next level. If true, we initialize both next level head and next level cur to this left child. Otherwise, we link the next level cur pointer to this child and move it forward. The same logic is applied to the right child, where we again either initialize the pointers or establish the next connection depending on whether next level head is already set. Once the left and right children of the current node are processed, we move current to its next sibling using the next pointer. After finishing all nodes at the current level, we shift our focus to the next level by updating current to next level head. At this point, both next level head and next level cur are reset to null, ensuring that they are ready to track connections for the following level. This process repeats until all levels of the tree are processed. Finally, we return the modified root, where every node at each level is now properly connected to its next right neighbor. This completes the implementation of the connect method. Here, we're given a simple binary tree, and our goal is to populate the next pointers for each node so that they point to their next right node. If there's no next right node, the pointer should be set to null. We start with the root node, which is 1. Initially, we set 2 pointers, next_level_head and next_level_cur, to none. These will help us track the head of the next level and the current node in the new level, respectively. At the first level, we process the root node 1. For its left child, 2, we set next_level_head and next_level_cur to 2. Then, for its right child, 3, we update next_level_cur.next to point to 3. Since there are no more nodes at this level, we move to the next level, which starts with 2, and reset next_level_head and next_level_cur. Now, at level 2, we process the nodes 2 and 3. For node 2, we connect its left child 4 to its right child 5. Next, we process node 3 and connect its right child 7 to the next available node, which is null in this case. After processing all nodes at this level, we move to the next level, starting with 4, and reset our pointers again. Finally, at level 3, we process nodes 4, 5, and 7. Since none of these nodes have children, there are no further connections to make, and we finish the traversal. The final tree structure with the next pointers populated looks like this. The root node 1 points to null since it has no next right node. At the second level, node 2 points to node 3, and node 3 points to null. Moving to the third level, node 4 points to node 5 points to node 7, and node 7 points to null. This completes our solution, where each node's next pointer is correctly set to its next right node or to null if no such node exists. The tree is now ready with the next pointers connected as required. To analyze the time complexity of our algorithm, we need to consider how the binary tree is processed level by level. The outer while current loop is responsible for traversing through the levels of the tree. For a binary tree with height h, this loop will execute h times. Now, the height of the tree varies depending on its structure. For a balanced tree, the height is proportional to log n, while for a skewed tree, it could be as large as n, where n is the total number of nodes. Within each level, the inner while current loop iterates through all the nodes of that level. Since each node is visited exactly once across the entire traversal, these inner loop iterations sum up to O(n) overall. Therefore, regardless of whether the tree is balanced or skewed, the algorithm processes each node exactly once, resulting in an overall time complexity of O(n) in all cases. Now let's evaluate the space complexity of this algorithm. Unlike other approaches that use auxiliary data structures like queues or stacks to manage level order traversal, this solution relies solely on a few pointer variables: current, next_level_head, and next_level_cur. These pointers allow us to traverse and manage connections between nodes without requiring additional space proportional to the size of the tree. Additionally, since the algorithm is iterative and not recursive, there is no recursive function call stack to account for. The use of a constant number of pointers means that the space usage remains fixed, irrespective of the tree's size. Thus, the algorithm achieves an optimal space complexity of O(1). Comparing this optimized approach with a more naive solution highlights its advantages. A naive method might involve using a queue to perform a level order traversal. While this would result in the same O(n) time complexity, the space complexity would increase significantly. Specifically, the space usage would depend on the maximum width of the tree, denoted as W. In the worst case, for a complete binary tree, this could reach n/2, leading to an O(n) space complexity. In contrast, the current solution eliminates the need for such additional storage by directly linking the next pointers during traversal. This allows it to achieve the optimal O(1) space complexity while maintaining O(n) time complexity. The efficiency of this approach, particularly in terms of memory usage, makes it well suited for processing large trees where conserving space is crucial. When solving this problem, there are a few common mistakes to watch out for. First, some assume that the tree is a perfect binary tree, meaning all levels are completely filled. However, the problem explicitly states that the tree is not necessarily perfect, so this assumption can lead to incorrect handling of edge cases, like when nodes are missing at certain levels. Another common mistake is failing to reset pointers for each level. If you're using a pointer to traverse the next pointers at the current level and forget to reset it for the next level, it will result in incomplete or incorrect connections as you move down the tree. Finally, some solutions unnecessarily use extra space, such as queues, to track nodes at each level. While this works, it increases the space complexity to O(n), even though the problem can be solved with O(1) space by leveraging the tree structure itself. Another mistake to avoid is incorrectly traversing the next pointers. Some assume that these pointers are already set up for all nodes and try to rely on them to traverse to the next level. This doesn't work because the next pointers are being established during the traversal. Using them prematurely can lead to logical errors. Additionally, overcomplicating the solution is a frequent pitfall. Writing code with too many nested loops and conditions not only makes debugging harder but also makes your solution less clear and harder to explain during an interview. Keeping the solution simple and structured will help you avoid unnecessary bugs and ensure that your logic is easy to follow. Now, let's focus on key insights for interviews. This problem is essentially a variation of breadth-first search, but it adds the challenge of connecting nodes in place while optimizing space usage. To achieve this, you can use a two-pointer pattern. One pointer, often called dummy, is used to manage connections at the next level, while another pointer, current, traverses the current level. It's also important to be prepared for edge cases, such as single-node trees, left-skewed trees, or trees with missing children at various levels. In terms of complexity, the optimal solution has a time complexity of O(n), since each node is visited exactly once, and a space complexity of O(1), as no additional data structures are required beyond the pointers. When explaining your approach, focus on how the next pointers are established and how you efficiently transition between levels. Clear communication is as important as the solution itself. Finally, let's connect this problem to related problems and alternative approaches. LeetCode number 116 is the perfect binary tree version of this problem, where all levels are completely filled. Other related problems include LeetCode number 104, which focuses on finding the maximum depth of a binary tree, LeetCode number 103, which involves zigzag level order traversal, and LeetCode number 199, which requires capturing the rightmost node at each level. If you're exploring alternative approaches, you could use a BFS approach with a queue to store nodes level by level. While straightforward, this uses O(n) space for the queue. Another option is DFS with recursive backtracking, which can be elegant but has O(h) space complexity due to the recursion stack, where h is the height of the tree. The most efficient solution uses the optimized pointer approach, leveraging next pointers to traverse the tree level by level with O(1) space. While this method is harder to implement and debug, it's the most space-efficient solution to aim for. Great job! To wrap up, we reviewed the key steps and concepts for solving this problem. Remember, mastering tree traversal techniques is essential, and problems like these are great practice for interviews. Thanks for joining me, and I hope to see you in the next session. Don't forget to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!